So it's a great pleasure to have here today Mark Dodici, who will stay here for the rest of the winter. Hopefully that will be the end of the winter. And he's a grad student in the University of Toronto who works with Sgr A and Galactic, and he works on dynamics of different channels of dynamics, I would say, but today he will tell us about dynamics of stellar binaries in the centers of galaxies. So take it away.
All right, thanks more for that introduction. And let me just start by saying I'm really honored to be giving this seminar. I was asked to give the seminar about 48 hours ago. So if at any point the pacing feels a little off, just feel free to yell at me to speed up or slow down. So as Maura mentioned, I'm a graduate student at the University of Toronto. I work primarily with Yanshin and Scott Permain. I'm here working with Scott through the end of March, and my office is over in the modular office spaces, which is a trap to get to from here. But I'll be here for coffees and focus. So if anything strikes your interest, I'd be happy to talk about any of this a lot more over the next month. So we're talking today about stellar binaries in the centers of galaxies. So we need to start by talking about what's in the center of a typical galaxy. And one of the key features of the centers of many galaxies of Milky Way mass are supermassive black holes. So these are objects that are 10 to the 5 to 10 to the 9 solar masses, and they dominate the potential of the area surrounding them and really sort of set the stage for a lot of the dynamics we'll discuss. And surrounding these black holes often are nuclear star clusters, and these are very dense environments, very dense clusters of stars. So in a few parsecs, you'll get roughly the mass of the massive black hole in stars and stellar remnants. And these clusters also have very high velocity dispersion. So if we think about the galactic field, we're thinking about velocity dispersions of order a few kilometers a second. Globular clusters, you may get up to to about 10 to a dozen kilometers a second. In the centers of galaxies, we commonly see hundreds of kilometers a second. And yeah, that also is sort of key to some of the dynamics that we'll be talking about. So yeah, these are incredibly dynamic environments. And we can focus on our galactic center. That's a picture of the black hole in our galactic center, Sagittarius A star. And our galactic center also has a nuclear star cluster around it, or around this massive black hole. And within about two to 3 parsecs, we see roughly the mass of Sagittarius A star. Also, because our nuclear star cluster is so much closer to us than all the others, we can actually observe some structure within it. So the structure includes a sort of disk-like formation of young stars that probably formed about 2 to 6 million years ago. There's also sort of an isotropic cluster of B and A type stars between internal to that disk mostly, but sort of overlapping with that disk. We also see a few dusty objects, which are sort of surprising, and we see a plethora of X-ray binaries, about 16, which suggests, based on some modeling, that there are a few hundred of these X-ray binaries, black hole X-ray binaries in the galactic center. So
we assume that the lower mass stars are just there but not seen, or for some reason are not
yes.
there.
So through modeling, we can constrain that the IMF of particularly the disk of young stars is top heavy. So there are most of the masses in the more massive stars, but there are certainly lower mass stars there that we cannot see in, I would say, all of these populations. So I'm talking today about binaries, and the reason for talking about binaries is that binaries near these massive black holes, and particularly the one in the center of our galaxy, are importantly related to several observable phenomena that have been sort of popularized over the last 10 to 20 years. So one of these hypervelocity stars comes from the disruption of binaries around that encroach too close to the massive black hole. This disruption also gives us stars on very tight but eccentric orbits around the black hole. So these are possibly the genesis of the S stars. We also see binaries in the galactic center, and it's useful to dynamically model that population to understand why we see the distribution of binaries that we do see. We see these X-ray binaries, as I mentioned, And we also see gravitational wave mergers of compact object binaries. These maybe merge in the centers of galaxies. So
we resolve binaries in the center of the galaxy?
yeah, so there are, well, sorry, we don't resolve them, but we can determine that they're from spectroscopy. We see the radial velocity of these binaries, or of these stars, are anomalous and inconsistent with a single star picture.
If we have B stars that we see, so basically every B star we have in our area has some M dwarf very close to it in the binary. So why shouldn't I assume that every B star you see there is a binary?
They don't appear to be.
You wouldn't see that.
Sorry.
Every B star here has an M dwarf.
Right. Right.
Roughly. So I would assume that every B star you see there has an M dwarf close to it. Why wouldn't I?
That's a reasonable assumption. And I think binary formation and star formation itself in a galactic center is a difficult process to constrain. And
what is the key difference between star formation there and here?
Well, there's a strong tidal potential induced by the massive black hole that can that sort of constrains the outer limit of where you can have binaries. And then if you do form binaries, those wider binaries are going to tend to be disrupted over time through interactions with other single stars in the cluster. An excellent point. So I'll talk briefly about some of the observations of binaries in the nuclear cluster. So as I mentioned, there are a few spectroscopically confirmed binaries. That number is 4. And based on those 4, some groups, and particularly this is the result of a group at UCLA that's done a lot of work to try to infer the population of binaries that's actually present in the cluster. And these are the constraints they end up with. So the purple distribution is the probability density of a particular binary fraction among young stars for stars within the central arcsecond. So within the central, about 0.04 parsec. And then the green is the same distribution for stars outside the central arcsecond.
Sorry, this is the model for the probability that a star is in a binary, depending on.
So this is the these distributions are the probability density functions of having a particular binary fraction.
So this is like the posterior on the binary fraction.
Exactly.
Some population model.
Exactly. Yeah. So a key element to this inference is the distribution of these binaries, so the semi-major axis distribution. And a key assumption that these works are making is that that semi-major axis distribution looks quite similar to the one in the field. And that is, again, because we don't really have good theoretical constraints, and we definitely don't have good observational constraints on the semi-major axis distribution in the galactic center. That's an assumption that I would sort of throw into question. But based on the 4 confirmed binaries in the central parsec, the general conclusion is that the binary fraction is lower, closer to Sagittarius A star, which I don't think is terribly surprising. So we also see these dust-enshrouded objects. The first one of these was detected in 2012. It's a gas cloud that's orbiting Sagittarius A star. There have now been a handful of other dusty objects identified in the galactic center with compact, optically thick envelopes that sort of span up to an astronomical unit. The origins of these are still unclear. Some of the early theoretical explanations were that these are the remnants of mergers of binaries. So these binaries, so if you take a stellar binary and you torque it with the massive black hole, as we'll talk about much more throughout the remainder of this talk, you can reduce its barycenter separation drastically to the point that you may merge the 2 stars and be left with an object that through that dynamical interaction has sort of kicked out a thick envelope. But they could also be, pre-main sequence stars that are still forming. They could be outflows from high mass stars that are losing a lot of mass through stellar winds. And there's sort of these handful of objects, there's little consistency between the objects. So it's not clear that these dusty objects actually all have the same origin in the first place. Yeah.
Okay, maybe it's not feasible yet, but so there are luminous red novae, that's like a similar phenomenology in external galaxies. Is there a reason to think now that they are biased towards centers of galaxies? Perhaps our horizon for detecting them is not that far off yet.
That's a good question and something that I don't know anything about, but something that I should know something about.
I think that they're only detectable in Andromeda, basically.
Okay.
They're not detectable any further out, so. But I don't know if there's any bias towards them being close to the center of Andromeda.
Yeah, that is definitely a number that would be useful to know. Moving on with this phenomenology overview. So we also see as I mentioned, some X-ray binaries in the central parsec. These are black holes with stars that are close enough to, or in close enough orbits around them to be donating material onto those black holes, and they shine in the X-ray through this accretion. Based on the 16 observed, which are circled in this Chandra image in teal or cyan and this sort of pink color, based on whether they're quiescent or variable. Based on the 16 observed black hole X-ray binaries, folks have inferred a population of a few hundred. It's not surprising that there are compact objects in the galactic center. There should, in fact, be many of them. But it may be surprising that you have these compact object main sequence or compact and non-compact object binaries, just because the binary lifetime in this environment, as I've sort of previously alluded to, can be quite short. You may be able to produce a good number of these X-ray binaries through tidal capture, so taking a single compact object and throwing a single extended object past it, inducing tidal oscillations in that extended object that damp out energy or damp out the relative energy between those two objects and result in a bound binary. And this process may be able to get you most of the way to the inferred population, but there are massive uncertainties in all aspects of this process. Compact objects may merge in binaries in the centers of galaxies. I won't spend too much time on this slide. I guess I'll just emphasize that there have been a lot of theoretical models for how compact objects may merge in both active galactic nuclei and non-active galactic nuclei. And conveniently, almost all of these studies end up with a rate that's sort of consistent with the observed rate. So if you look at the error bars on these red and blue theoretical models and compare them to the error bars on these observed, on the observed population rate, you'll notice that there's a good amount of overlap. And this may be a little too convenient. There are 1,000,001 knobs to turn when you're making these population census models. So some of the work that I'm doing hopefully sort of constrains one of those knobs, which is understanding the population of stellar binaries that may survive to post-main sequence evolution, if any. Some things that I'm really interested in are hypervelocity stars. So I mentioned if you throw a binary too close to the massive black hole, the tidal potential of that massive black hole will tear apart those two stars, will rip them from each other. And if that happens when the binary was initially on a nearly parabolic orbit, then typically one of those stars will be ejected and will gain enough velocity to escape the potential of the black hole and perhaps even the potential of the galaxy, and the other star will remain bound. And the ejected star can have a very large velocity. As I mentioned, there's only one observed hypervelocity star that we can confidently say came from Sagittarius A star. It's about 2.5 solar masses. It seems to have been ejected about 4 to 5 million years ago, which you may recall is also roughly the age of the young stellar disk in the galactic center. So that's maybe an interesting coincidence. And it was ejected apparently at about 1,800 kilometers a second. So that suggests that it came from a very tight binary to begin with.
Yes, and we know it's from Fuji star because of the trajectory.
So just backwards modeling the trajectory that from the 6D parameter space that we currently observe it, or parameters that we currently observe it to have, we backwards model in galactic potential.
We discussed with Coffee some time ago a paper highlighting that there are multiple high velocity stars, but some of them cluster in a region that seems to come from the Magellanic Clouds, and another one seems to come from the Sagittarius star.
Yeah.
So I'm surprised to hear that there's only one.
Yeah, me too.
So there is a broader population of high velocity and hypervelocity stars that are observed in the galaxy. It is true that there was that paper that claimed that a lot of them are coming from the Magellanic Cloud.
When you say there is one confidently coming from Sagittarius A star, what do you like about that one?
I guess I like how small the posterior is on where it last crossed the galactic disk.
You take its kinematics, you trace it back in some galactic potential, and how close does it come to the center?
Like the posterior covers the center, and I think
Whereas none of the others even get anywhere near.
yeah.
Those ones in the LMC or wherever they.
No,
It was a
forget the
separate-
LMC. There are some
It was separate.
really good
Those
ones.
distance measurements are so difficult. Like this one is one where you actually have really good 60.
Yeah, so the convenient thing about this one that I'm highlighting, it was observed sort of by chance by SDSS, S5, which is not SDSS.
But there was this SDSS one that was a really strong candidate like 15 years ago, 20 years ago. You don't like that one.
I don't like
never
it.
mind.
I think the 2020s literature does not tend to like any other than this one, but I definitely concede that there is a broader population of velocity stars that may have come from the galactic center. The sort of consensus is that this is the only one that we can confidently say it definitely came, well, as confidently as we can say anything was definite in astronomy, it definitely came from this very narrow region centered on Sagittarius A star.
But for the other ones that are very high velocity, is it that there's another explanation, or is it that because of the error bars we cannot pinpoint, but for the most part, nobody came up with some other explanation?
Yeah, so generally they all have much lower velocities than this particular example, which is another reason why this is sort of the most confidently associated with the Hills mechanism in Sagittarius A star. So the others are of order 500 kilometers a second ejection speeds or lower, which I think is more in line with what may be possible through supernovae kicks in binaries, or through other sort of scattering processes, or even from like globular cluster ejections of high velocity stars. But the other byproduct of the Hills mechanism are these S stars. So as I mentioned, in this process, one of the stars is going to get left behind on this highly elliptical, very short period orbit. S stars may be examples of these sort of left behind remnants. As I mentioned, that's the sort of isotropic cluster internal to the disk that's observed in the nuclear star cluster. And then in other galaxies, we've started over the last 5 or so years to identify what seem to be repeating partial tidal disruption events. But what may be more observationally classified as just repeating transients that are localized at the nuclei of their galaxies. So these tend to have baselines of half a year to tens of years. There are also this class of transient event called quasi-periodic eruptions that tend to have much shorter periods, which may also be related to this implantation, but particularly for the repeating partial TDEs, these are stars that seem to be on short period high eccentricity orbits that are consistently coming back close enough to the tidal disruption limit for that particular star, such that part of their mass is stripped off at every paracenter passage.
How many are these?
The repeating partial TDEs?
S stars, identified S stars at high eccentricity orbits.
Identified S stars is about a few dozen.
So each one of them has a twin that is running out.
So that would be the result if all of the S stars came from Hill's mechanism. It's not clear that all of the S stars did come from the Hill's mechanism, and but yes, if this is true, if this sort of hypothesis that S stars come from the Hill's mechanism is true, then yes. And similarly, the hypervelocity star may have had a twin within the S star cluster, and people have looked for that twin, have not confidently identified any sort of twin, but also have various dynamical pathways by which that twin might have been destroyed in the intervening about 5 billion years.
And is there a clear prediction for the eccentricity distribution if this hypothesis is correct among S stars?
Yes, and generally the thing that this theory struggles with is taking that predicted initial eccentricity distribution, and which is hyperthermal, so more eccentric than thermal, and reducing it toward the more thermal eccentricity distribution that's observed of the S stars. So this is definitely not a sort of concrete explanation for where the S stars came from, but it's one of the sort of suggestions in the field. The other, yeah. So again, we have all of these observables that are related to the centers of galaxies, that are related to binary stars in the centers of galaxies. And to really constrain these observables and to really make the most of continually improving observations of these phenomena, we really need to understand how these stellar binaries evolve in time. So if we start with some initial set of conditions for a binary population, how will that binary population change? And the way to think about this, or the way to start thinking about this, I guess, is to think about all of the possible effects that can act on your binaries and to ask what timescales they act on. So I'm here plotting on the horizontal axis just the outer separation from Sagittarius A star. So I'm going to focus on a binary with 10 AU semi-major axis with 2 stars that have the mass of the sun in a Milky Way-like galactic center. I've plotted just sort of for visualization the mass or the main sequence lifetimes of stars of various masses. And then in this plot, I've also shown the outer orbit period as a function of separation and the inner orbit period of this 10 AU binary. So right away, I mentioned that if the binary comes too close to the massive black hole, it'll be disrupted. That's a tidal radius. So that's sort of the minimum separation that it can have. One of the key effects that I'll be talking about over the next half hour is the von Siepel leadoff Kozai effect. So this is a result from standard hierarchical triple dynamics, where if you take this setup, you have an inner binary and an outer orbit of an object moving around, or an object and the center of mass of that inner binary moving in a Keplerian orbit, and you average over the period, you average the potential felt by the inner binary from the outer perturber over the periods of both the inner and the outer orbits, then you end up with these oscillations in eccentricity of the inner binary. And these eccentricity oscillations are going to be sort of key to a lot of the dynamics that I talk about for the next part of the talk. And we can see that this timescale, the timescale of these eccentricity oscillations, so basically the period of the cycles, scales like the outer semi-major axis cubed, and it scales also, which is not shown here, but it scales as the inner semi-major axis to the -3/2 power. So strongly dependent on outer semi-major axis, a little less strongly dependent on the inner semi-major axis, but still definitely faster for wider binaries. We can also write down the evaporation timescale. So as I mentioned, these binaries are constantly perturbed by other stars in the cluster. And because the velocity dispersions of these clusters are so large, these perturbations will tend to widen the binaries over time. They're what's known as dynamically soft. And so we can write down a characteristic timescale on which these binaries will become so wide that they will be broken by one further kick, basically. And so that evaporation timescale looks something like that for a Milky Way nucleus. And we can see that there's this large region of parameter space where the von Siepel leadoff Kozai oscillations are much faster than the evaporation timescale. So right away, we're sort of getting a sort of hierarchy of these dynamical effects we'll be considering. One of the other aspects of dynamics that I'll focus on is resonant relaxation. So in this nearly Keplerian potential at the center of the galaxy, orbits, these outer orbits are going to be, again, nearly Keplerian orbits that are going to precess over some timescale that's much longer than their orbital period. So first they will, so because we have these nearly Keplerian orbits, over the timescale of precession, all of the combined effect of all of the other orbits will tend to relax our target orbit. Will tend to change its scalar angular momentum, and that happens on the scalar resonant relaxation timescale, which we can see is much longer than most of the effects that we're considering. And on a much shorter timescale, a different sort of form of the same sort of process will tend to reorient these outer orbits. So this is vector resonant relaxation, which basically relies on the fact that because the potential is spherically symmetric, even when your Keplerian orbit precesses, it's going to precess to form an annulus, an annulus rather than precessing, rather than forming some form of torus. And these annuli will sort of also coherently torque each other. But the result of that torque is not to change the scalar component of the scalar angular momentum, but rather to change the orientation of that angular momentum vector. So this timescale is going to be independent of binary semi-major axis. And we can see that for this particular binary, it's roughly comparable to the evaporation timescale throughout the cluster. And then in the outer reaches of the cluster, it'll also be comparable to the von Siepel leadoff Kozai.
These processes are sculpting the inner binary parameters, right?
So that's a very good point. So the von Siepel leadoff Kozai and evaporation timescales are particularly affecting the inner orbit parameters. The resonant relaxation processes are affecting the outer orbit parameters. There are other processes affecting the outer orbit, like two-body relaxation, which we heard a lot about in the dynamics meeting this morning. But that will typically take longer timescales, and timescales as long as the Hubble time, and definitely longer than the evaporation timescales for most of these binaries.
There is no tightening process? I mean, when you evaporate, you can also tighten. So it depends on the initial.
Yeah, so as I mentioned, because the velocity dispersion is so high, these binaries tend to be soft, and the sort of standard result, the Heggie-Hills law, tells us that when a binary is soft, its Keplerian velocity is, roughly speaking, its Keplerian velocity is lower than the velocity dispersion. Interactions will tend to increase its semi-major axis. So very few of the binaries in this nuclear star cluster are going to be the opposite, are going to be dynamically hard. So those would tend to shrink.
What about those that were falling at the backhoe and the parabolic? They are very tight.
Yes.
This is what makes the hypervelocity star.
Yes.
So this very small population that you're saying, most of the binaries are not these binaries.
Yes.
But they have some signature of the ejection.
Well, there may be other ways to tighten binaries, which I may be about to discuss. So GR precession of the inner orbit or the outer orbit. It'll affect both. So the inner orbit will be caused to precess, or the argument of periapsis of the inner orbit will precess due to general relativistic effects, and also due to tidal bulges and rotational bulges raised on each of the stars. And at times those can suppress these von Siepel leadoff Kozai oscillations. And that's something that's self-consistently accounted for in the remainder of this talk. And then there is also general relativistic precession of the outer orbit, and that mostly is what keeps the scalar resonant relaxation time so high in the very inner regions of the cluster. in the outer regions, the scale of resonant relaxation timescale is high because
They folded into that SRR times.
yes, yeah,
It always takes the Newtonian precession at the minimum.
exactly.
Connecting to Mark's presentation, so all of your timescales are much shorter than what he was talking about. So that because two-body relaxation was what controlling the basic density profiles. It was
Yes.
so
Yes,
you're talking about all of your processes are much faster.
yes. So an important caveat to all of this discussion, and something that we've sort of touched on in this introduction, which I meant to take about 10 minutes on, and instead of taking about half an hour on. I should have known. An important caveat to all of this is that we don't actually know how binaries form in the centers of galaxies. We don't know what our initial conditions should be. We have a few simulations that purport to sort of study infalling clouds of gas as they get into a galactic center and follow star formation and binary formation in those infalling clouds of gas. We also have sort of an understanding of how nuclear star clusters are built up, both from in situ formation of stars from infalling clouds of gas and from the early sort of infall of globular clusters, which through dynamical friction will tend to move toward the center of the galaxy and there sort of become disrupted and end up making up the early parts of this nuclear star cluster. And so we can sort of put together a picture of what a binary population might look like. But any picture that we actually try to put together is going to be wildly uncertain. And so for the rest of this talk, I'm going to try to stick to results that are sort of generalizable and don't really care too much about our initial conditions of our population. So again, we just got through a rather lengthy introduction. Next, I'll talk about some work that we submitted and should be published soon. That the gist of is that many binaries in these nuclear clusters should shrink to near contact separations and should actually, in some cases, become hard binaries, even though they were born very soft. And through this, we'll talk about some perturbed triple dynamics. I'll go on an aside that I'm now not sure how long I'll spend on. That'll be on diffusive tides and the tidal friction that comes out of fully considering dynamical tides. And then I'll show some simulation results and some rather naive point models. And then at the very end, if there's time, I'll talk a little bit about how active galactic nucleus stages of these galactic centers may be very important in sculpting this binary population. So before I do that, are there any more questions?
It's a dangerous statement.
Okay, I'll move on. So the big middle of this talk is summed up in this one slide. So 2 in 5 stellar binaries orbiting Sagittarius A star, so within the nuclear star cluster, should shrink to near contact separations before leaving the main sequence, before they die. And this is work that's on the archive. You can take a look at it, and I'm happy to discuss it at any point over the next effort. So there are 2 broad steps to this shrinking. So first, I'm going to discuss how dynamical effects acting on these binaries are going to reduce paracenter separations of these inner orbits to roughly 3 stellar radii for a solar mass star, or just very small generally. And then I'll discuss how tides raised on the binary members, so the stars comprising a binary, will rapidly act to shrink those binaries once you get down to very small paracenter separations, and how this may lead to a population of very near contact binaries.
40% of within which radius, sorry?
Within about a parsec. I'll show a plot as a function of distance. So this sort of process is contrary to the standard expectations of binary physics. So the prevailing wisdom is that most binaries that survive until reaching post-main sequence evolution must have started very small, must have originally been born at these near contact separations. Rather, here we're saying that you can actually take a lot of initially soft binaries and turn them into very hard binaries. And the other sort of standard result from models like Alexander Stefan's work from the mid-2010s is that these von Ziepel-Lidov-Kozai oscillations are going to drive a lot of mergers. And instead, we're arguing that diffusive tides are going to mean that shrinking is a lot more common than merging among these binaries. So first we want to reduce paracenter separations to a few stellar radii. So as I mentioned before, these von Siepel-Leadoff-Kozai oscillations are going to change the inner orbit eccentricity of these binaries. And if we just take a very simplistic view of ZLK oscillations, so take the potential of the black hole to quadrupole order, we're going to get this maximum eccentricity that you can reach during the course of an oscillation. And this maximum eccentricity, if you start with a circular orbit, has this very simple form that depends on the inclination between the inner and the outer orbit. And of course, if you take the potential of the outer orbit to octopole order, then you may get variation in this maximum eccentricity, and that variation will happen on longer timescales than just one cycle. So sort of over many cycles, the maximum eccentricity will sort of decay over time. But we're not going to focus on octopole order effects because I would argue the other effects that we'll discuss will sort of dominate any benefit that we may gain from octopole level. So we can define this parameter space where on the vertical axis we have our binding energy of our orbit, and we're going to scale that binding energy by some characteristic separation. So we're interested in binaries that reach some critically small paracenter. So if we just take that critically small paracenter and divide it by some major axis, we get this vertical axis. And then the horizontal axis is just the z component of inner orbit angular momentum, or the z component, because I am a graduate student at the University of Toronto, which is in Canada, where they say z. We're just going to square the z component of inner orbit angular momentum and put that on the horizontal axis. And we can recast this maximum eccentricity into a condition in this parameter space. And we can say that if a binary begins with a small enough value of this script I, then it will be able to reach through just quadrupole order ZLK oscillations this critical paracenter, which again we've not yet defined. So again, anything starting to the left of this line will reach a critical paracenter. Anything starting to the right cannot through quadrupole order ZLK. And so this, we'll call it a ZLK loss wedge. It's sort of similar to the idea of a standard loss code. But the reason for calling it a wedge is that if you're sitting in here, you still need to complete one full ZLK cycle before you actually reach whatever critical paracenter you are interested in. So just reaching the loss wedge is not going to be enough to necessarily reach a critical paracenter. You have to stay there for long enough.
The x-axis is JZ.
Yes,
constant.
Square.
And the y-axis is a prediction of what paracenter would be attainable.
No, the y-axis is just the semi-major axis of the binary scaled by some critical paracenters. So say we want to know what binaries are going to reach a paracenter of 0.1 AU, we would put in 0.1 AU as our critical paracenter, and that would tell us where our binaries fall on this vertical axis. So if you are interested in say, a population of...
this is like Emacs.
Yeah,
Emacs.
it's yes.
Okay.
In a way, yeah. Yeah. It's one minus Emacs, yeah. Right. Well, no, sorry. No, because it's 1 minus the E that would be required to actually reach whatever critical paracenter you're interested in.
Big lines is 1 to 1. It's just saying the smallest you can go is JZ. J equals JZ.
Yeah.
So what I've said so far is that 40% of systems are going to shrink by reaching some critically small paracenter, but only 5 to 15% of our systems are actually going to be born in this green region. So how do we get more systems in? Well, fortunately, I'll mention that there's this other condition on this parameter space where if you become too wide, you're going to be unbound. And fortunately, we have plenty of dynamics at our galactic centers. So perturbations from passing stars are going to change all of the aspects of your inner orbit. It's going to change your semi-major axis eccentricity and inclination. So it's going to move you around this parameter space in sort of a heavy-tailed random walk process.
And what's your cutoff for becoming unbound? I suppose that's a convention, but
we take some factor times the inner orbit semi-major axis times the mass of the black hole over the mass of the binary to the 1/3. So just a scaled factor of the tidal radius. But also, if you just reach, you can also through these flybys just reach positive binding energy, and then you would also be unbound. So another process that will be sort of key here is vector resonant relaxation, which may reorient your outer orbit, changing the inclination between the inner and the outer orbits. And so while flybys are going to sort of take you on this random walk around this parameter space, vector resonant relaxation is just going to move you side to side. So one would expect maybe that if vector resonant relaxation is much faster than flybys, you'll tend to spend a lot more time going side to side than you will up and down in this parameter space. And that's beneficial because, again, up and down, you may end up becoming unbound, but side to side, you may only reach this critical paracenter, this region of parameter space where the ZLK cycle may bring you down to a critical paracenter. So based on those timescales that we saw at the top, we can define sort of this characteristic timescale ratio that's going to generally give us an idea of how systems should evolve in this parameter space. So the color map in this plot, we're looking at the semi-major axis of the inner binary and the separation from the massive black hole. And the color map here is the ratio of the ZLK timescale, so the period timescale, or the period of those cycles, over whichever is smaller of the vector resonant relaxation or the evaporation timescale. And so generally over in this very blue region, we have ZLK cycles that are very fast relative to the other processes. And in the green to yellow region, we have ZLK cycles that are very slow relative to these other processes. And the black line I've marked there is just a ratio of 0.1. So a ZLK cycle is about a factor of 10 smaller than the evaporation or vector resonant relaxation timescale. And the dynamical importance of these regimes is, at least the way I think about it, basically that if you're in this refilling regime, you're going to sort of very slowly walk around this parameter space. And at every point in your walk around the parameter space, or I guess I should say your steps can be large, but at every point in this parameter space that you sit, you're going to sit there for at least one ZLK cycle. And usually very many cycles. Versus if you're in the sporadic regime, you may jump around to a different place in the parameter space, but you are not necessarily going to sit there for an entire ZLK oscillation. So you're not necessarily going to reach the minimum paracenter associated with that particular point on this parameter space. So I should probably sort of speed through the discussion of diffusive tides, but the gist is that when the eccentricity of these orbits is very large, the main effect of tides raised on each of these members of the binary is going to be sort of a kick at paracenter. So during a paracenter passage, some energy will be deposited or taken from the oscillation of the stars. And the oscillations will focus on the sort of fundamental mode, which is the fundamental response of a body in hydrostatic equilibrium to a tidal potential. We'll focus on the fundamental mode, and this has some characteristic frequency, which we'll say is omega f. And the amplitude of this response, of course, depends very strongly on your inner orbit paracenter. So our critical paracenter that we've been alluding to is just the onset of diffusive tides. And what are diffusive tides? So again, the kinetic energy of this tide is going to be coupled to the orbital energy in that every time you give energy to the tide, you take energy from the orbit, and that's going to change the orbital period. And a result from tidal theory is that when the change in period from a given paracenter passage is of order the mode oscillation period, then your mode is going to grow diffusively. Your mode amplitude is going to grow as a random walk. And as a result, your mode energy is going to grow linearly with the number of paracenter passages. And this allows this is something that was shown in some numerical results and then sort of more well understood theoretically over the following decades. And the result of this is that orbital energy can be reduced very quickly. Now, what do I mean by quickly? So if we take sort of the standard ZLK and equilibrium tides picture, this is an example from planetary dynamics, so looking at hot Jupiter formation. But the standard sort of picture is that it takes many, many ZLK cycles to reduce your semi-major axis through this dissipative process. Whereas under diffusive tides, if you reach the critical paracenter, you can basically dissipate all of your orbital energy in just one cycle peak, in just one peak of your ZLK oscillation.
I think you haven't preempted that I've asked. I think you haven't mentioned at any point singly average fluctuations.
Sorry, what was that?
Singly average, non-doubly average. So there's the simple fact that eccentricity, once you get very, very high, is also oscillating, and that can blurs the edge of it. It's a bigger parameter space that'll lead to mergers. And then there's also this thing that we found called what we call relativistic phase-space diffusion. But basically, when you switch on a tiny bit of GR, you could jump from one set of intervals of motion to another.
Right.
It's basically going to take what we had for the flybys and just boost everything's going to random more, much more. Does that come in at a higher order than this effect? Is it not important?
Sorry, at a higher order than.
I wonder because we never included any tides. I wonder whether the tides actually swamp those effects.
Oh, so you're thinking about general relativistic effects in this in orbit.
In general, in your system, non-doubly averaged effects have some impact.
Right. I think my working assumption is that non-doubly averaged effects are just going to increase the fraction of systems that reach these very small these very small paracenters. And then once they reach these very small paracenters, the result is going to be that tides take over and acts to shrink the binaries. It is true that if the result of non-doubly averaged effects is to increase the sort of speed with which the paracenter separation is reduced, then that could sort of kill this in that you can
jump over this barrier, basically.
Right. Just move through the diffusive tide regime too quickly to actually stall and shrink, and you'll end up with a merger.
I don't know which is dominant.
Yeah, that's a. I agree that I need to look more into the singly average case. In the doubly average case, this is just a prescription for how the diffusive tide boundary goes with stellar mass. So it can be very small. For very small inner orbit semi-major axes, and for stars just a bit more massive than the sun. And this just broadly reflects changes in stellar structure over the course of a spectrum of masses. So more extended stars or stars with more mass on their outskirts, the criterion is at a wider separation versus more centrally condensed stars. The criterion is at a smaller separation. Right, so this is sort of just an example of a ZLK oscillation throwing in this diffusive tidal evolution. But again, this is a doubly average ZLK oscillation, so not sure that touches too much on the single average point. I'm rapidly running out of time, so I'm going to speed through some of this.
We had plenty of questions in the middle, so please go on for a couple of minutes. I will just stop you right before the hour.
Okay, thanks. So we can make sort of these analytic estimates for when tides stop ZLK versus so basically when tides prevent mergers versus when you would expect a merger. So this yellow line is basically the limit where the time that you would spend below the time that you would spend with a paracenter separation equal to the sum of the stellar radii in an unperturbed ZLK cycle is equal to the time it takes for diffusive tides to reduce your semi-major axis by a factor 1/2. And so we argue that this reflects sort of a decent boundary condition for where shrinking will dominate over merging. I would say the boundary is certainly fuzzy, and we need some more rigorous numerical simulations of this effect. but that's sort of our analytic understanding for where that boundary should be. Then we can also say these tides are going to induce some precession. So where does this precession dominate over the precession that sort of sets ZLK oscillations? Basically, where do you detune the ZLK oscillation? And that gives us this blue boundary, which apparently is not as important as the pure energy deposition boundary, but down here at very small outer orbit separations may become significant. So neither of these is a perfect condition, but generally, if this is our available parameter space of binaries, I would say that, and up here, binaries are unstable to the tidal potential of the massive black hole. I would say that most of the binaries fall below one or both of these conditions. Yeah.
Can you emphasize again the difference between the setup in the galactic center and hot Jupiter formation? Because hot Jupiter formation, some of the hot Jupiters, so you may say that hot Jupiter formation is shrinking, but maybe many Jupiters just merged with the star and didn't shrink.
Right.
So is there like an inherent difference between the two setups?
There is not, other than which objects' tides sort of dominate the process. So in hot Jupiter formation, it's tides raised on a Jupiter mass object, and in this, it's tides raised on a star, but otherwise it's the same dynamics.
Okay, so sculpting the hot Jupiter population was the study before things were known about the galactic center, or observationally about the galactic center. So this was not discussed in hot Jupiter science?
It has been, and I think since about 2018, I think it has become the concept of diffusive tides shrinking, or diffusive tides being sort of the dominant dissipative effect in hot Jupiter formation is becoming a more prominent view. In
This is because the galactic center was studied?
No. So I think that my work and paper that I'll mention briefly are that was also published last November, are the first to consider diffusive tides in the context of the galactic center. So hot Jupiters came first in terms of where we considered diffusive tides, but okay. Sorry, so we have these two broad steps to shrinking. ZLK and perturbations are going to reduce your pericenter separations, and then once you reduce your pericenter, diffusive tides are going to lead to rapid shrinking of the binary. Then we can do some simulations of binary stars orbiting Sagittarius A star. So these are going to be double averaged quadrupole ZLK with a toy model for vector resonant relaxation and impulsive flybys from single stars. And then we're going to end when either we reach the critical pericenter separation, which we say is a proxy for shrinking to avoid having to actually do the mapping model of the diffusive mode growth. That's something that may be useful for future work. But so an important caveat, I guess, is that we are just considering any binary that reaches the critical pericenter separation to have shrunk rather than to have merged. So we can end either then, when the binary is disrupted, or when the binary leaves the main sequence. And
Maybe you should start wrapping up.
yeah. Okay. So there's our fraction of binaries that should shrink as a function of separation from Sagittarius A star. This is where the 2 and 5 number comes from, so that's roughly there. And we can, so I guess the 2 and 5 is a bit of a clickbait title, because we really don't know what the binary distribution should be at all of these different separations. It likely varies. There may be far fewer binaries here than out here. So maybe the fraction is really 1 in 5. But if we just wanted, or if we ignored flybys and all the rest, then we would just get these systems that start in the ZLK wedge. If we considered octupole or non-doubly averaged effects, that fraction would be slightly increased. But we can see that flybys and vector resonant relaxation are really driving an increase of this shrinking process. We have sort of a simple statistical model that matches the results well that I'm not going to talk about, but there's one parameter that we need to tune, and it's fairly straightforward to tune. Just as sort of quick evidence that this ZLK loss wedge is actually important, every binary that shrinks on our simulations or that reaches the critical pericenter does in fact come within a factor of 2 of this critical boundary, which is not terribly surprising, but just nice validation that even when the timescales of flybys and vector resonant relaxation and ZLK are all comparable, still what we're seeing is that things shrink when they reach this loss edge. And so that sort of informs the statistical model that I skipped through. Based on the statistical model, we can sort of create these mock populations of the semi-major axis distribution. So if we don't consider ZLK or tides and just consider flybys, our semi-major axis our binary population is going to be rapidly reduced. By the time we get to about a gig a year, we're going to have basically no binaries left. If we do include this effect, this shrinking effect, at full levels of optimism in terms of how efficient it is, then we instead get this sort of spike of long-lived, very compact binaries in the galactic center. So what can we say about our observables? Many things, but also not much because of those uncertainties in the initial conditions. So we can try to constrain some initial conditions by comparing or by using this dynamical model and comparing with observations of binaries. As mentioned, there are only 4 binaries observed. These shrunken binaries are probably going to undergo common envelope evolution, so it's not clear if they will survive to be compact object binaries. One interesting thing that I haven't really explored too much is that these hardened binaries, so the binaries that shrink in the outer reaches of the cluster are become dynamically hard through shrinking. And so you can have these interactions where you throw a single compact object binary or a single compact object toward one of these now hard binaries and exchange out one of the stars in that binary for a compact object. This could be a possible source of X-ray binary information, but again, I haven't explored that too thoroughly. And the sort of really interesting result, I think, is that these shrunken binaries are going to give us much faster hypervelocity stars and much closer in S stars. But with typical sort of loss cone relaxation prescriptions, I think roughly half of not a large fraction of binaries that are disrupted are going to be disrupted from this population of binaries within the central parsec. Most are going to be a little bit further out, so around the sort of radius of influence or a little further. So I'm not 100% optimistic that this will give us faster hypervelocity stars, but the work that I'm not going to talk about, that is next, suggests that AGN disks may sort of help us disrupt some of these binaries. But I'd be happy to talk about that at a later time. I think for now I should probably stop. And I'll just pretend that I only gave the first half of this talk and leave up that as my conclusion slide. I'd be happy to take any questions. And again, I'll be here for the next 2 months or so. So just shoot me an email if you would like to chat at any later time. Thanks.
Okay, so thank you, Mark. We had plenty of questions already. So if you want to ask Mark anything, he's right here. Yeah.
Yeah,
That's it.
shut up, people.
Exactly.